FPGAs. And my research interests are at the intersection of security and performance, and also supervisor operation modes, such as Intel SMM, that I think a lot of people here are quite familiar with, the Intel SMI transfer monitor, STM, that I'll be talking about today, virtualization, firmware fuzzing, and also rootkit detection. So a group of varied interests, but yeah, today I'll be focusing on the STM part. So I'd like to give like a short SMM, STM intro recap. I presented some of this back in March, so I'll try to keep it real brief, but just to kind of level set, I'll just share a little bit about just background. And then I'll talk about some of my efforts recently in enabling the STM on Dasharo, and then just a kind of a quick example of how you can use that capability to protect your operating system or VMM from unchecked SMI accesses. And then open it up for a little bit of discussion around this topic. So as everybody knows, firmware is widely present on a variety of devices. On x86, the most important runtime firmware is system management mode. It's actually an x86 execution mode. And this is essentially, I think of it as a second side of the platform. And so on one side of the platform, we have our applications, operating systems, hypervisors. But on the other side, we have this SMM code that's also resident. But essentially, we can take these interrupts that take us from the host side into system management mode, either periodically or asynchronously. And once we do that, we transfer into code that's very highly privileged. And essentially, it's traditionally had access to the full CPU register state, the ability to change MSRs, the ability to look into memory and control devices. And so that presents a number of concerns if you're trying to think about how do I build a defendable system where SMM and SMI handlers that I've never seen before are in the TCB, the Trusted Computing Base. And there's also a risk of, there might be valid SMI handlers, but they could be buggy. And, if they have vulnerabilities or they could be coerced into doing improper things, that could have impact on the rest of the system. So, as we think about SMM security, I think we talked about this a little bit last time. There's just a variety of things to consider, all the way from architectural to secure coding to how it's configured, and then, are there issues in the software implementation? So I'll be talking about STM coming up, I think, in about 2 hours-ish. Rowan from Intel, one of my colleagues, is going to be talking about a new CMIX-based fuzzing. So we probably want to stick around for that. But basically, SMM security has a wide variety of things to think about. And so as we look at the STM, like one of these architectural mechanisms, essentially this is a way of providing a protection policy over SMI handler accesses. And so this gives us the ability to reduce the risk of improper SMI handler accesses. And how does this, or what does this do? And so the STM basically provides a policy that it enforces over that SMI handler code. And so this policy is directed by the OS or VMM, and the STM enforces it. But essentially, it provides ways to specify particular memory regions or MMIO regions, CPU MSRs, IO ports, PCI devices that we want to keep the SMI handler from being able to access or modify at runtime. And so depending on the system, that policy could be implemented in different ways. And so for some systems, it could be a very light policy. For other systems that want more refinement over SMI handler accesses, the policy could be more involved. So the STM is also open source and enabled in Core Boot. And so that made it kind of interesting to enable here on the Dasharo. So if we think about traditional SMM, we add in Intel VTX virtualization, then we get the STM. And so basically the STM operates as a peer hypervisor So it's a peer of the host side hypervisor, but with the difference that it operates in SMM, and it has as its virtual machine the SMI handler code. And so just like we run Linux or Windows in a VM on the host side, the STM runs the SMI code in SMM. And so as I set out to get this working on a test system, I very thankful to all the hard work that Eugene Myers did, who laid the groundwork for this in core boot through the STMPE project. And so, a lot of the plumbing was there and the capability, but there's still a few things to address, as I wanted to get this working on the MSI Z690A board with Dasharo. So some of the things I ran into and needed to fix were the STM binary itself. The core boot uses a slightly different version of this code base that's been enabled for core boot, and building with GCC, it ended up with a larger STM binary size. And so, that ended up causing a little bit of a challenge when we needed to fit in this STM binary into the firmware volume. And so thanks to Dasharo for coming up with a way to expand the CBFS to fit the larger STM binary, and that worked. And also there were some efforts that I need to do to configure some of these SMM regions, including like MSEG, where the STM resides. And so just adjusting a little bit of the core boot config options and kind of fine tuning a little bit to find something that would allow the STM to fit into memory, and then have a large enough tseg to incorporate this. So that there was a little bit of kind of fine tuning on that effort. And then there was also an issue to be resolved that a new core boot has a fix for, that has to do with SMM memory alignment, that was initially causing a hang during the first boot after loading or putting that STM into the BIOS and running that. So it wouldn't get out of the boot process, but there's a fix for that now. And as you go to launch the STM, there was a minor issue with one of the resource descriptors, and there's a patch pending for that. And so, bottom line, the groundwork was there, but it needed a little bit of fine tuning to fit into something that would run on the Dasharo board. Along the way, it was helpful to have that BIOS serial output capability on the MSI board, and interfacing that with the RTE was super useful. After you bump up the amount of serial logging that core boot is doing, then you get this real heavy flow of BIOS logs coming out. And there's some great instructions from Dasharo on how to connect those jumper wires between the RTE device and the MSI board. And then basically, once you SSH into the RTE, and then you can capture all of those logs from the BIOS boot, and even save them and export them. So that was a very helpful capability. The STM has its own PCIe-based serial card that you can use. So as you configure core boot, you can specify the IO address of that serial card. And so that way you have distinct logs from the STM as well as the rest of the BIOS being outputted to separate sort of serial consoles without them sort of being all mashed together. So that was pretty helpful as well. And then along the way, I also, soft breaked my platform a few times. So having this ability to do the BIOS flashback capability was super useful. I probably used it 10 or 15 times to get this working. So if this wasn't there, that would have been a lot more work to do hardware sort of BIOS flashing recovery work. So, all these put together made for a very capable development environment to bring the STM online. And so once we have the STM, it's actually dead code until we go and turn it on. And so one of the things that I tried out was this launch of the STM. And that essentially is a sequence of VM calls that is done by the hypervisor. So VM call is just an Intel VTX CPU instruction where the less privileged environment can call into the more privileged environment for some sort of service or some sort of API. So normally, like a Linux virtual machine might have a VM call to the hypervisor to do something. In this case, we have the host side hypervisor doing a VM call to the STM. And so that is the mechanism that we use to launch the STM. And there's some launching code that has been written by the community. The Linux one, Eugene Myers from the STMPE project has published, and it's based also on a launcher that was done at Portland State University for Zen. And so with these two launchers, we're able to launch the STM, in Linux or in Zen, for example. And as you launch the STM, there's a variety of serial logs that get outputted. And here's just a small sample, but you would expect to see, if you build a debug one, something like this as you're bringing the STM online. And just to show like how the protections might work, this simple example does a protection of one MSR. And so the launcher code is also responsible for providing a protection policy that it wants the STM to enforce. And so essentially, it allocates one or more pages and creates kind of a back-to-back layout of these resource descriptors on that memory page. And it has the terminator at the end. And so, here's an example of one resource descriptor that requests the protection to prevent the BIOS SMI handler from writing to this particular MSR. And so the flow to incorporate that would be, we run this hypervisor launch sequence, and there's actually several VM calls that happen, but the one that's important to this example is before we bring online the STM fully, we've kind of pre-provisioned the policy that we want the STM to enforce. Normally, if we had a TXT capable system, then SMIs would be quiesced at this point, and so that would be sort of even better. But since this board doesn't support TXT, we have to do this protection request, while there could be some SMI activity. But basically, we do this protect resources VM call, and that provides this policy to the STM. The STM inspects the policy, makes sure it's sane in terms of just, it's the integrity of that protection request doesn't break any rules. And it will then go, the STM will then go and configure the MSR bitmap for this SMI VM. And so from now on, anytime that VM tries to touch that particular MSR, it will cause a trap down to the STM. And so that is, a mechanism to keep that SMI code from being able to, in this case, improperly access a resource that was not granted to it via the policy. And so, to test that out, I made a small change to the core boot SMI handler, where if I write a specific value to port B2 from a kernel module, it would then, this additional code I added, would then go and try to write values to this MSR. And so, if this capability worked, we would see this message, which is what I saw. And so, this is an example from the STM serial log of it capturing and trapping on that access. And so that's kind of an example from, how we can use this capability to protect, things like MSRs, IO ports, memory regions, etc. from full access by SMI handlers. We want to keep this short for some time for discussion, but to conclude, STM provides a new mechanism that's not really being used today to basically give additional protections against problematic SMI handlers. And these SMI handlers could be buggy, or they could be malicious, if somebody were able to compromise SMM. And so this STM is built on an open source code base. It's freely inspectable. You can look at the code. You can see how it operates. So it gives you sort of a root of trust that you can look into and understand. And the way it operates is it uses just normal Intel VTX capabilities, just like we use in the host side virtualization. And it will basically just maintain and apply that protection policy over those SMI handlers at runtime. And so this gives us the principal of least privilege for SMI handler code, and also some defense in depth in case there is some issue with an SMI handler that we weren't aware of before. And Dasharo, the firmware and the test environment was super useful in having all of the various capabilities that one would need to sort of enable this feature. As I think of the other platforms I've used, the only thing that's missing maybe is like JTAG, but in terms of everything that one might want, between the serial logs and the BIOS recovery capabilities and the ability to flash that BIOS, that was all there. So that was quite useful in bringing this capability online. And we haven't really talked about it, I think, as much here at some of these Dasharo meetings, but there's also sort of a parallel effort run by Eugene Myers for STMPE, which is a way to do protected execution using the STM VMs as well. So for those who are interested, you might check that out. It's something kind of like a trusted execution environment that uses the STM to run different VMs, each with different protection policies to put workloads in more secure locations. So that's essentially a new capability that we wanted to have a little bit of discussion about, and just see, is this something that sounds interesting? Does it sound useful? Are there questions about how it works, or anything else that we can discuss? I have a list of resources here that go into more detail for those who are interested. There's some good articles here on SMM protections in general for, in this case, UEFI. We have the STM spec, a pointer to the code, the community launchers, and a paper we did back in 2020 at HASP, and some information also on other SMM protections from Intel.
Well, that's really great. I love the presentation. I love the concept. I have some notes and like tons of questions that I can easily probably use next 30 minutes. But I would like to start with community. If anyone from community has questions to Brian.
Maybe just one question from me. What would you see more beneficial to Coreboot, SMI transfer monitor or PPAM?
So I think they have kind of different purposes, although they do basically reuse the same CPU capability, in that they both are operating in that SMM peer monitor role. And so they're both VMX roots in SMM, and you have to pick one or the other currently because there isn't a interoperability standard between STM and PPAM. But PPAM is all about reporting, and so it will give you sort of reports about how your SMI handler is configured, what accesses it has. But it's also today quite tied to vPro platforms, and so it hasn't been enabled, at least as of this talk, for open source or yeah, or it's not something we could just test out today on like Dasharo, for example. So, and the STM, of course, is all about resource protections at runtime. So, yeah, I see them as kind of two different capabilities that both happen to use the same CPU infrastructure.
Yes, that is why I'm trying to get at to the question whether it is even does it even make sense to implement vPub in open source firmware?
I think there may be less, I mean, just personally speaking, there might be less value in sort of reporting a capability because you already kind of may be able to sort of derive what accesses your SMI handlers will be doing because you have access to the source. But for a lot of vPro platforms, if you think of a typical platform from like HP or Lenovo, you don't have like an open source firmware there. So you're not really sure exactly what is happening in SMM. And so in that case, having a report out, that's trustworthy, would have more value, I think.
Yeah, but on the other hand, it is the firmware that actually reports the hashes of SMM via the vPub manifest, right? So
Yeah.
how can we trust something that claims to have such a footprint if we cannot verify it?
Yeah, I mean, I think it comes down to, how do we build our trust assumptions for these platforms? Do we assume that, because we buy an HP platform that we trust HP's report? I think there's different questions that come up. But yeah, I think there's sort of two different paths towards getting more protection or introspection capabilities into your platform. And some of them may make sense more for vPro environments. Some may make sense more for open source firmware environments. I guess that is kind of a question to think about.
Yeah, I think it would be more trustworthy if the vPub was the module that calculates the footprint of the SMM instead of rely on the claims done by the firmware itself. I may be missing something here because I haven't gone too deep into the vPub details.
The reason why people ask for the firmware to say something like that is the same reason why, for example, the government will ask you to attest to something you are doing. They're not going to check yet, but you're legally signing off that you think this is the truth. So when Microsoft asks a firmware vendor to do something like that, it's kind of a precursor to a stronger assertion later on. If you think about it, it's not the truth. It's a contract between Microsoft and their provider, their supply chain vendor, which is the IBV. It's got a very different. It's not a technical thing. It's a legal thing.
Yeah, I guess this
thanks.
chain of trust, root of trust.
It's part of secured core. Remember, it's part of the trademark secured core.
Yeah, so Michał, I guess our perspective, open source firmware perspective, is a little bit different. Brian, are you still with us?
Yes, can you hear me?
Okay, yeah. You just disabled the camera. That's fine. I have a couple of questions. Like one of the questions is, I wonder if STM is not like something that we can clearly advertise to offensive researchers as a means to explore code that tries to leverage SMI vulnerabilities. Is it can support the research of the malicious code that tries to leverage SMI problems?
So, I mean, STM is basically, it's just like a hypervisor in a way. And so I think, if you think of the malware analysis that happens on the host side, some of that, could be done with virtualization. So I would think that, a lot of, low-level platform security researchers would find something like the STM quite interesting because it would allow them to run the SMI code in a kind of in the virtual machine. And with Intel VT, you can do a lot of things. You can single step the execution, you can trap on certain things. So I think there's a lot of interest. I think, I think it would provide a lot of interesting capabilities for people who are interested in sort of better understanding the workings of the SMI VM, for example.
Okay, yeah. So you know where I'm going. I'm still kind of searching for the value for the open community. Let's say for example, like we will have some Dasharo version on MSI. We will join your work with some, I don't know, special version of Dasharo. But we have to say someone like what kind of use case this.
Well, there's a collection of SMM exploits, right?
Yeah.
In theory, the STM is going to block all of them. In theory.
Yes, that's my point. If we can prove that as a demo, that's kind of value. Yeah, this value. And I guess like you're talking about the crash famous exploit.
You could. I don't know if there's a framework. I don't know if Chipsite could do it, but I mean, you could almost collect all those exploits and call them test cases, and just do an STM test framework, or SMM test framework, right?
Yeah.
And then.
Yeah, that's also something that we talk with Brian directly, like that this still needs testing. Yeah, Brian.
Yeah, so I did want to mention this. We haven't. This hasn't been run, in production. So I think there's still a lot of validation that would need to happen around this capability. It was released as kind of a reference implementation. So yeah, I think definitely some testing around this would be quite useful.
Other kind of segue topic. Can we like another like marketing idea? Talk with CubesOS people and talk that by adding STM we will have like MSR firewall, or like your example of we can control like who access which MSRs, and we can protect some access if we don't like it. And like we added we have like CubesOS certified device with STM Dasharo, and that's like just adding capability which is called MSR firewall.
So what's an example MSR that somebody might want to block?
Brian?
Well, so I mean, one of the MSRs that's pretty important is this one that actually protects the STM is 9B. So that one has to be protected. And in this case, we already have that sort of in place because we're using it, and the STM will do its own protections for that MSR. But there could be some, if there were some tracing MSRs, or I think some of the ones that might adjust some of the control flow, I think those might be interesting. But I think, one of the things to think about is, what is the set of protection requests that we want to make, and how do we validate those? And so I think, sometimes we want to take a look at what are the SMI handlers actually using, and what do they really need to function, and then what is the other set of MSRs that they have access to but aren't really using. But that, that's sort of a non-trivial amount of work. I mean, it has to be sort of thought through about, what MSRs should be, actually prevent access to. For memory, it's a lot easier because you can sort of carve out and say, I kind of know where my operating system memory is, and I know like what memory Zen is using. And so, actually with some of the EDK2 changes that have happened in the last few years, they'll actually unmap a lot of the host side memory from the SMI handlers, because they shouldn't be accessing that anyways at runtime. So I think memory is kind of the easiest one, but then it comes down to kind of rationalizing about specific MSRs, for example. And also the STM does have a feature where if the virtual machine on the host side has potentially some values in its registers, in its general purpose registers, because maybe it's doing some key handling, and there may be some sensitive values in those registers. There is a way with the STM to scrub those register states before processing the SMI. And so that's called the protected domains feature of the STM. So that's also one other sort of capability that's available. So I think memory regions are the clearest cut answer. And then I think maybe thinking about, what are some MSRs that we are concerned about from the security perspective, and let's scope those out and see if that makes sense to do protections over.
So like those AES encryption acceleration related registers, or I don't know, SGX, or
well, some of the more advanced like crypto processing technologies, might not expose some of those values to registers, kind of by the way they were designed. But if somebody has kind of rolled their own sort of application where they're doing cryptography, they got keys and registers, then I think that's more of the risk. And so if somebody is aware they have that type of operation or that type of application, then they might be more motivated to protect the register contents from their SMI handlers.
Mm-hmm. Okay, so maybe let's move on to another potential value chain. I guess like trench boot and DRTM area is something. So I guess like STM at some point would be must with trench boot. Like, are you familiar with trench boot? Like,
I haven't looked as much at trench boot, but this is it's like a TXT platform. Is that correct?
It's essentially open source version of tboot, but cross vendors.
Okay. Mm-hmm. Yeah. So TXT. Well, STM was originally designed for TXT, and it actually, like the SNIT modules, the ACMs from Intel, are fully aware of like the STM, and they'll do STM provisioning when they see that there's a valid STM that's been configured. So
what does it mean? What does it mean?
Yeah. So because the STM, well, traditionally the STM is launched in 64-bit mode, which means that we need page tables created before we even jump into the STM. And so for TXT platforms, the SNIT module will go and create the 6 initial memory pages for the STM, so that it can kind of bootstrap the STM and have those memory pages ready to go as we jump into it. So that's something that the SNIT module does. It'll also do a cryptographic measurement of the STM code section, and it'll populate PCR 17. So that's available. It will also quiesce SMIs at, I think, getsec senter until the STM is turned on. And so we can kind of guarantee that there's no SMIs firing while we're trying to bring up the STM. And so there's, I guess, long story short, there's some additional goodness that one gets by using the STM with TXT. And you get kind of the more full implementation of the STM. But because, just practically speaking, it's been harder to have sort of a vehicle for people to try out the STM, because vPro platforms that allow you to sort of build an STM are not really very common. I think initially STM was sort of released for the Intel Middle board, if you remember that little tiny motherboard. Yeah, so that's a non-TXT platform.
Yes.
So some of those initial capabilities they had to build into the BIOS just to get it, like those initial page tables created, which can hurt some of the security assumptions, because you're using the BIOS to create the initial page tables for the STM, when normally the SNIT module would be a better place to do that because it's more trustable. But just practically speaking, that was just kind of a compromise that had to be made to get the STM working on sort of commodity non-TXT platforms.
So I think, Pierre, you have one or two vPro platforms have been identified which can support core boot.
Yes.
So do you want to mention those?
Yeah, this one was this Lenovo M920Q, and other was that we tested the trench boot recently, which was this HP. Damn, I don't recall, 800 something.
Okay,
So
these are best business, they're business class products, right?
Yes,
Client
yes.
devices. So we could potentially, someone could try to get the STM and Dasharo and Core Boot on those devices.
Yes, and I think, Rich, the even bigger value is in the platform where we cannot put, like, if Brian will tell me if this is like even remotely possible. When we cannot put Dasharo, but we add STM with Trench Boot as a UEFI applications, and then we have, let's say, CubesOS, and we have anti-evil mailed thanks to that. Even on the platform when underlying firmware is like potentially SMIs are, like problematic or may have some issues. Or this
right,
is like,
but how can you add the UEFI firmware to those platforms?
yeah, you can like just add the UEFI FE files, add them to the boot process, to the boot variables, and like kind of configure that to kick in before anything else. But yeah, maybe I'm just dreaming. This is just rough idea. Because Rich, the problem is that when you know the content of SMIs, like in Dasharo, you know the content of SMIs. Unless FSP will or some other binary blobs will start to install SMIs, they do this. They don't do this right now. Then this STM is not huge value. It's like different value than protection against malicious SMI. Yeah, for open platform, for trustworthy platform, for Dasharo like Coreboot like solution. The value of STM, my understanding, is where the BIOS is closed and these SMIs are potential source of issues. Yeah. Just tell me I'm wrong.
Well, I think it also comes down to, like, sometimes there's vulnerabilities in code that we're not aware of, and so at least this is a way where if something is discovered later that causes unexpected host side memory access, this is one sort of safeguard that we that could be put in place, where we just have a policy that no SMI handler is able to touch this range of memory, for example. So that way, if something later does happen, then we have kind of a safeguard. Just to clarify one point earlier, this is using the Core Boot STM, and so you could actually, if your platform is Core Boot only, you could use this capability. There's no EFI dependency in that case.
Does the STM use any hardware related to nested virtualization?
No, it just uses, if you have VTX, then you have an STM capable system. None of this is using any nested virtualization. I'm sure people get creative and do more advanced things, but no, as currently instantiated, it's not using nested virtualization, just pure VTX,
okay.
Standard virtualization.
So Brian, so there is possibility to have STM as a UEFI application.
Well, initially STM was developed and showcased for UEFI, and so there was some sample UEFI BIOS code that loads the STM and provisions MSEG and sets MSR 9B and the various things you need to do to put the STM in place. So there's, I think, an older code base that Intel open sourced that's available on a GitHub for people who want to take a look at that. But yeah, the STM itself is a binary. It's just it's not even like a UEFI file or anything. It's kind of a binary blob essentially, but it gets built from Core Boot during the compilation process in this case.
Yeah, where I'm going with this is that, let's say, Dasharo Core Boot plus UEFI, like we're running this one, and then in the boot process we can kick just for validation purposes, kick the STM from UEFI as a UEFI application, and then kick Zen hypervisor and make it work together to protect against those future undiscovered yet vulnerabilities. And that's one path. And in the same configuration, you can try to do the same thing with this proprietary BIOS-based solution. Like, tell me if if I'm missing something, that this is not possible, or maybe there are some limitation that this cannot be done.
I think as long as you're able to basically, carve out a memory space to store the STM and, provision the right MSR that points to that address, and do that from SMM, then you have the building block for a place for the STM to stand, and then you can instantiate it, just from a VM call, with VMX root permissions on the host side. But I think you do need to be able to, modify the BIOS such that it's at least programming this MSR 90 from SMM mode and carving out these memory regions that you need, and creating initial page tables. But yeah, if you have that ability, then you've given the STM a place to stand, and it's up to you later how you want to kick it off. There's actually an example Intel released called FRM, which loads the STM. What does this? So instead of the hypervisor that's shown in purple here, that you could infer was like Zen or something, Intel has a UEFI-based hypervisor that was called FRM that would actually go and do these VM calls, and so it could actually be instantiated like during the platform boot up sequence. So after the STM had been kind of configured in memory and the opt-in bit set, then this STM launcher UEFI hypervisor would run, and then it would do the VM calls to turn on the STM. So yeah, I think there's a lot of flexibility about how and when you turn it on, but the initial provisioning has to be done from SMM.
Yeah, I understand that. So that means like some certain lock-in is not made by BIOS, or at least we can enter the like UEFI share or whatever. We can somehow enter the land where there is no. I guess the exit boot services is the place where typically all this locking will take place. So if we can be either before exit boot services or somehow, yeah, I guess like this is like trying to find a platform with firmware that gives this ability to enable things if those are not enabled out of the box. And as you said, like most likely they will not be enabled out of the box. Yeah.
Right. Yeah. So you're going to need something equivalent to what you can do today, I think, with being able to provide different memory size ranges. Like I'm doing it today with this .config file, for the Dasharo core boot config file. So just being able to kind of specify these different ranges and make sure those are in place, as you're copying this STM binary into that location.
So I will tell you like this, like I have this feeling after all these years doing the BIOS related stuff and security in BIOS, I have a feeling that every time we're trying to leverage advanced security in the open ecosystem, we face this situation where we essentially need compliance, a kind of test suite or something, which can check if this hardware, because we really don't know how this BIOS was, mangled, and we really don't know if this is like, if we can do something with this hardware, what we want, like enabling STM. So we have to like compliance framework for checking if UEFI secure boot can be provisioned as we want, checking if the DRTM can be leveraged as we want, checking if the STM can be leveraged as we want. So this is like, I have a feeling that there is huge value in having this kind of framework. You will tell me ChipSec, yeah?
well, ChipSec does a certain set of things, but you might be asking for something even broader. So maybe there's another box down here below ChipSec. Yeah, I think ChipSec is very focused on are the right lock bits set. They have some CAN tests to make sure that the BIOS is configured in a way that looks somewhat secure. But I think you're asking even, for like, could we tell if this platform could run an STM? And it's more than just looking to see if that CPU supports VTX, because
this is exactly it, because I can buy a bunch of hardware and I have then stock of hardware, like it's already in 3MDEP, like I guess you probably got the same. A lot of hardware like sitting there because like at some point someone realized, okay, it will not work for my use case because, and there is no way to ask your vendor about that. There's no way about that. Nobody will tell you if STM will work with this BIOS. You have to buy hardware and test it yourself, or find someone who will like run some quote unquote suite to verify that.
So I have an idea around this. I actually have an idea for a subscription site to put all the information that the vendors would never give you, which would actually save people money because you can spend $5 on the subscription site instead of $500 on the hardware that may or may not work for your needs. And have that subscription site have a business model to afford the hardware to test it, so you have you can trust the assertions.
Yeah, that's very good. Like that's very good. That's something what we need, because then we have a lot of these advanced features, and we will say have the same with AMD, because we don't know if with this curtain model this feature will work. At some point we faced the bug in NXP boot ROM when we didn't know if the verified boot will be secure or will not be secure, because certain boot ROMs got the vulnerability and certain not. And even the seller, when we go to the seller, to someone who represented inside the NXP, couldn't tell us which series will have fixes in the boot ROM and which not. Yeah. So that was also kind of like in this realm of, does this hardware can meet my security requirements and can mitigate my threat model? Yeah.
Well, the best part is the people on this call collectively probably have, 100 devices.
Probably, yeah. Or more. I definitely more. Definitely more. 100 is probably like 3MDEP. Or more, I guess. Okay, last thing I want to mention, because like we have last 5 minutes, I wanted to mention, I don't know, Brian, if you heard about the Ron Minich talk. It's kind of old talk. It's called "Let Move SMM Out of Firmware and Into the Kernel." Did you heard about this talk?
I might have, if this was one of the, I've heard of similar efforts like at OSFC. I think I've heard some of this.
Yeah. So I guess this is very close to kind of what STM, I guess, did in some. It's already done, but essentially this idea are already there and in various ecosystems. Like even like I guess like assuming that the core boot ecosystem like 10 years ago or 15 years ago was not exactly unified ecosystem, but these ideas are always there, and I guess there is potential for synergies between open ecosystem and UEFI forum and even closed source IBV to enable stuff like STM and to make it work and create a hardware and deliver BIOS for hardware, so STM can work without this corner cases that we have to verify before we even buy something.
Yeah. Well, I think like some of the work you're referring to is maybe in this attack surface reduction capability or category. So I think there is a set of work that's happening today in the industry about like looking at all of the SMI handlers and trying to think, is this one that really has to be an SMM, or is this something that we can offload to some other place? And so I think, as part of a holistic view of security, that is sort of a whole, that's something to think about. I think one of the nice things about like the core boot side that I've seen on the Dasharo platform is there aren't a ton of SMI handlers actually. I mean, it's not like there's a lot of like, a huge number of these SMI handlers. So I think the attack surface is probably smaller. So
Can you say something a little bit more about this SMI handlers that you saw by using Dasharo? And I guess like this community would like to hear a little bit more about that. If you recall, like what was the purpose of that? What those accessing? How you look at the security of those and trustworthiness of those?
Some of the ones that I saw were kind of like the chipset SMI handler functions, like I think the TCO one. I noticed like there's an SMI that happens every, I don't know, 16 seconds or something like that on the board. That's a TCO SMI, I believe. And then there's some like the ACPI SMIs I think I saw. But, you know, I would say that UEFI has a lot more complex SMI handlers, like the lockbox and the variable handler. You know, the code complexity of those is quite large. And so I didn't notice those on this platform. So yeah, I think there's a difference in some of these very large SMI handlers that take sort of complex, untrusted inputs. And that's where, you know, like I think Rowan will be talking in a little bit about some of the fuzzing efforts. I mean, that if you think about like what's a good candidate for a SMI handler to fuzz, SMI handler to be fuzzed, you know, then it's probably one of those that takes these inputs like the variable handler, the lockbox, you know, those types of things. But, you know, simple SMI handlers to just set bits, you know, there's not a whole lot to fuzz. So yeah, I think there is also, I guess, a concept of how complex are the SMI handlers in use. And if they're just setting registers, you know, then the code complexity is pretty, you know, small. And so you would anticipate it would have a lower attack surface. But then again, on the other hand, there's some examples of some very complicated SMI handlers too out there. So.
Okay, so Demi.
Can you say a little more? I'm not particularly familiar with that one.
So this one was reported against AMD. So, but against AMD SEV SMP. But I have it on somewhat decent authority that there is a similar problem with SMM, and that is cache non-coherency that can be induced by the OS via a write back via some cache maintenance instruction. I think it's NVD or WB NVD, one or the other, something like that, and therefore can be used to escalate privileges.
Yeah, I haven't looked at that one in detail. But I guess STM isn't really focused on caching, so I don't think anything in STM.
Oh, STM has nothing. The question is about SMI. The question, I think, the argument is that as long as this instruction is present, then SMM is inherently insecure. Cannot be. Then, I guess STM still protects against attacks from SMM, but it also means that attacking SMM is possible reliably, and that the OS can, the question is if the OS can use this to reliably escalate privileges to SMM. And
yeah, I'll punt that one back to the community, maybe, given that it's about one of our competitors. So yeah, I don't know.
The question is if the same thing applies to Intel also, because the instructions found both places, I think.
Yeah, I mean, I'll just say that you know, if you're the owner of your STM, you know, you could add in various flushings, you know, that you want to do, I suppose.
That's a good idea. You
also have, I guess, control over the SMRR caching, you know, at your availability.
Okay, and this may not work on Intel, but I'll see.